All right, chemistry, I'm going to talk a little bit about significant digits. We also call them significant figures, or short, you just call them sig figs. This should line up with your assignment for the week and that worksheet trying to figure out how many significant figures are in a value or a measurement. So there are a couple rules to remember. They take a little while to settle in, but they're not bad. Okay, so the first rule, the easiest rule for counting sig figs in a value is anything that's not a zero is always significant. So you don't have to worry about those, you just count them. So that 7, sorry, this is hard, it's backwards for me. That 7, right, the 4, and the 2 are all significant. Okay, the next thing, any trapped zero, any zero between two non-zero values is also always significant. Okay, so the 0 right there is significant because it's trapped between the two 4s. Okay, and then here's the hard one, because zeros are kind of difficult because sometimes they are significant, other times they're not. Trailing zeros to the right of a decimal point are always significant. Okay, if they are zeros to the right of some values but they're not to the right of a decimal, then they're not significant. Those are called placeholders, and we're going to talk a little bit about that in a second. So those 3 rules will get you by. If you count up those digits, starting with the 7, ending with the 2 zeros at the end, all of those are significant. I think there's 10 in that value. So that is 10 significant digits. That's a very precise number. A number that, with that big and that precise, is kind of rare in chemistry. Usually we deal more in the 3, 4, 5 significant digits when we're making measurements. So let me switch over to the whiteboard. I got some values up here. So what we just kind of talked about were zeros, okay? And so the first one might be good for a machinist. If you're a machinist, you're a metal worker, you're in Miss Adams' metals class, you guys might have to measure something down to 50 thousandths. Now, the bottom to me looks like 50 thousandths of an inch, and it's written 0.050, and above it, 0.05. Now, to math, to Mr. Patterson, those two numbers are equal, and Mr. Patterson would put an equal sign between them and call them the same thing. But to a chemist, to a machinist, those are not equal. Well, they're equal, but they're not equally precise. And so the one below, with the 0 at the end, that is 1 digit more precise. This has 2 significant figures, okay, which would be the 5 and the 0. Okay, and that 0 counts at the end because it's to the right of a decimal. Right, to the right, it's a trailing 0, it's at the very end of the number, and it's to the right of the decimal. Okay, these zeros are not significant. I could put here, not significant, because they are placeholders. All they're doing is showing that that 5 goes in the hundredths place. Okay, it doesn't go in the tenths place, it doesn't go in the thousandths place. It's just shifting the 5 left and right. Okay, so those ones are not significant, but the 5 and the 0 at the end are. Up above, just the 5 is significant because it's the non-zero value. Again, the 2 zeros in front are placeholders. Okay, now think about this one. I looked up the average weight of a car, and you're thinking, okay, those numbers, maybe one car weighs 2,800 pounds, the other one weighs 2,803. Okay, here's the crazy thing, right? Chemists, when they see this number, they think that this was weighed on a scale that was only good to 100-pound increments. Like it might read 2,700, it might read 2,800, it might read 2,900, but it always bounces between these values. You've seen that if you go to the transfer station, their scale doesn't read down to the ones place. It just kind of estimates and rounds within the hundreds place. Okay, so this has 2 significant figures. Okay, and the zeros at the end are not significant because they're not after a decimal place. They're just trailing zeros, and they're showing placeholder. They're putting the 2 and the 8 in the correct spot in that number so that it's a value of 2,800. If you didn't have those zeros there, it would be a value of 200 or 28 or 280. Okay, but the zeros give it a place and an order of magnitude. The 2,803, you guys would never go to the transfer station, drive your car up on the scale, and see it read 2,803 because that is too precise. This actually has 4 digits of precision, or 4 significant figures. And this 0, you're wondering, okay, Mr. Ford, that's not to the right of a decimal, but it is trapped between the 8 and the 3. Without that 0, you'd have a completely different value. That 0 is acting as a significant piece of the precision, 2,803. So this one we could say is like twice as precise as the one up above it because of that 3 at the end. Now, you're wondering, how do I take a value? What happens if I weighed something on a scale 2803 or 2802 or 2801 and 2800, and you're thinking, this has 4 sig figs, this has 4 sig figs, this has 4. Well, how do you show that 2800 2800 has 4 significant digits? You do it by throwing a decimal in. Okay, what the decimal does is it kind of acts as a trap. It traps those zeros, and without the decimal, it's got 2 digits of precision. With the decimal there, it's got 4. With some extra zeros, maybe this was $2,800, 0.00, with no pennies, no nothing. This is precise down to the hundredths place. And now, because you put trailing zeros out at the end, then you've got 1, 2, 3, 4, 5, 6. And you're thinking, Mr. Ford, you just said those weren't significant? Well, now they're trapped between significant digits. The 2, the 8, and those trailing zeros are significant. Well, then those 2 in the middle have to be significant as well. So this has a total of 6 significant figures. So by adding zeros out to the end, you show more precision, right? This means if this was, again, a car, think about this, and a car drove up and it really truly read 280.00. Okay, that's, you can't say exactly 2,800 pounds, but it's very precise to 2,800 pounds. If a car drives up on this scale and it reads 2,800 pounds, you're thinking, well, I kind of know it's somewhere between 2,900 and 2,700. I don't know exactly, so I don't know as much precision, okay? And you're like, okay, this is a lot to do about nothing, but why in the heck would I care about this? So I'm going to just show you a quick little demo. Let me switch back over. I'm going to unplug my phone, or I'll do this. I'm going to move some scales over for you. All right, we'll let it warm up. Okay, this is reading, oops, 0.00 grams. It's been zeroed or torn. That T is for tear. Okay, and so if I weigh my pear, this pear weighs 274.03 grams. 274. Oops, it's fluctuating. 274.06. Okay, I'm going to set this back up. 274.06. Which is precise down to 5 significant figures. And then I've got this scale. I'm going to do the same thing and just show you. This is actually from my kitchen. This one was from the Chem Lab. This one's from my kitchen. Okay. Oops. Got to get out of the time setting. And this again. Zero. Oh, it's not a very flat surface. 0. There we go. And it's reading 0.0. Okay, oops, and that's ounces. 0. Unit. There we go, this is better. Oops. This is reading 275 grams for the pear. Okay, so I'm going to go back. Sorry that took so long. It's hard to do things with one hand. I am going to try and get a GoPro. That's my next investment. And then I can wear a chest strap and we'll see how it goes. Okay, so this one, 275 grams versus 274.06. This has 3 significant figures. And you're like, okay, well, what's the big deal again? They're within a gram of each other. Now, when we start, determining how many atoms are in a sample, how many molecules, maybe we want to know how many molecules of sucrose, fruit sugar, are in this pear, and we do some different tests and analysis. The more precision we have on the initial mass, the more precise we can get to the counts of certain molecules, the concentration of sugars in here, the concentration of different vitamins. And so by starting out with high precision in measurements like mass, we're ultimately going to get high precision in our answers. And the goal of science, right, is to be precise. Now, within reason, you could probably pay thousands or tens of thousands of dollars to get really nice scales and equipment. But we don't need to be precise in high school chemistry, especially with distance learning. I'm going to be happy if you guys can get a bathroom scale that can weigh in grams or kilograms, because that might be all we get. It's going to be hard to get supplies to you guys and have you guys do all this stuff. So you usually have to pay for precision, and you don't always need it. So this, with the 3 digits of significance or 3 digits of precision, is good enough for things like baking, for when you are Gordon Ramsay and you're weighing out your flour, right? Because British people always weigh out their ingredients, because measuring the volume in a cup changes because the density of flour changes. So Gordon Ramsay weighs his stuff out on a kitchen scale, and 3 digits of precision is good enough for him. And chemists, right, who are making solutions, or doctors who are testing different pharmaceuticals, they use more digits of precision and finer equipment. Now this is an Amazon special. It's not necessarily expensive, but it does have a more precise sensor, force sensor inside of it that gives 5 digits of precision. Okay, later on, we're going to be doing stuff like when we calculate density. Oops, and I've lost my pen. When we calculate density, if you only have 3 digits of precision in your mass or 3 digits of precision in your volume, well, it turns out your density can only have 3 digits of precision in the answer. So when you start doing math, which we're going to do next week, and you factor in precision now, you always ask the question in algebra class, well, where should I round to? Should I round to the tenths, the hundredths, the thousands? Turns out there are special rules that scientists use. They're very logical rules that help you round so that you are not too precise or overly precise, and you're not falling short of your precision. So we will talk about that next week. I'm rambling. Hopefully this makes a little sense. If you guys are still confused on digits of precision, I'll probably throw out some more hints and stuff next week. But for now, that's a good start. And then we got to talk scientific notation and some other factors. But again, I've thrown a lot at you first week, so good luck. Stay positive. Let me know if you're having trouble with the worksheet. I will post a key up tomorrow, or probably you're seeing this Thursday evening, like towards dinner time. You can check your answers. You can submit what you've got by Friday, and then I will have a quiz up. So watch for the quiz stuff. All right. See you later.